Let's recall what the spring constant is from physics. We know that K is supposed to equal weight divided by distance, which is the same thing as saying newtons over meters, or it's the same thing as saying pounds, lbs, over feet. So if we had a hanging object with the spring here, then there'd be some point right here where we would first attach the object, and then it would start to pull the spring down and end up somewhere over here, so that we can sort of call this little shift from here to there, we'll call that delta x naught. And we can make a nice little equation that says mg is equal to k, that's the spring constant, times x naught. So we have our first equation for springs. Let's see what happens to the net force after we pull this object down another delta x. So we essentially have, our initial point there, and it hangs a little bit, so it moves this delta x naught. And then not only that, but then we're going to pull it down even further, and that's where we have our object there. We'll call this delta x, and let's see what kind of equation we can get. Let's try to rearrange this equation. We're going to put this on the left side, so we get sort of mg minus the kx equals 0, right? But instead of 0, we're going to call it ma. So let's see what the net force is going to be. We're going to start with our mg, right? And then we're going to subtract minus k. But now we've got a bigger shift here, so we're going to add x naught, and then we're also going to add in the regular x that we have here. And so now we have our equation for the net force after we pull this down some bit. Considering that mg equals kx naught, we have an mg minus kx naught, so that's going to go away. And then we're left with negative kx over here. So I'm going to write that ma plus kx is going to be equal to 0. Okay? And then we can divide this whole thing by m. So we're just going to get rid of it here, and we're going to divide it over here. And of course, acceleration is the second time derivative of position. So let's go ahead and rewrite this as dx, or d squared x divided by dt squared, second time derivative of x, plus k over mx equals 0. Furthermore, we can replace the k over m with w squared. And so now we actually have two equations we can use with this little formula. This is actually the ideal situation when it's free, undamped, and in a vacuum. And then what we'll be able to do is we can write our equation, our answer, xt, is going to be equal to c1 cosine of wt plus c2 sine of wt. If we were to consider a damped situation, we'd have the equation m, and then we have d squared x over dt squared. Let's go ahead and add the damped force, which is b dx over dt. Okay, this is the damping force right here, all of it. And then let's go ahead and add in the kx, which is over here. This will be equal to 0. And if we have a damped spring, it's going to look something like this if we were to look at the graph. And we'd be able to flatten out this curve and make it look a little bit more like a regular sine wave if we have our original equation here, and we just set this equal to ft instead of 0. And we're going to be able to call this the impressed driving force. It's kind of like a little generator that's keeping this equation constant, and so the equation will look kind of more like a regular sine wave again, like that. A couple more quick notes here. If we have x of 0, that's clearly going to be our starting point, because that's when time equals 0 at the very beginning. And we might have x prime of 0. Well, this would just simply be the initial velocity. And then let's also not forget that g is usually supposed to be equal to 9.81 meters per second squared, but it's also equal to 32.2 feet per second squared. 32.2 feet per second squared, just in case we're using feet. Now let's discuss series and how they relate to differential equations. So a series, we'll start with a y, assuming that y is equal to the sum, n starts at 0, goes to infinity, and then we have some an and an x to the power of n. So that's where we're going to start our assumptions that our solution is equal to that. Now I haven't put any equations up here, but the idea is that you're going to want to plug your y's into your diff EQ. Okay, so like for example, over here, you got your second derivative, your first derivative, and then your regular y. So we have our regular y right here. For y prime, we're going to take, start with that sum, n equals 0. Then we're going to take n and multiply it at the beginning there, and we have a sub n, and then we're going to have x to the n minus 1. For y double prime, that's going to equal to, again, the sum. We're going to take n, and then we have this n minus 1. We have the a sub n, and the x to the n minus 2. So we have all three derivatives that we would be able to plug into a differential equation. Your next goal is to align the powers of x to the n. So you have x to the n, x to the n minus 1, and x to the n minus 2. When you plug that into some equation, you want to make sure that they all have x to the power of n, so you can add them all together. Let's do a quick example of how we might be able to transform the second derivative to the x to the power of n. And I'm going to start by writing x to the n right there because that's what I want. And then I'm going to try to figure out, where does this begin from? Where does our n start? Well, if we plug in n equals 0 here, we get x to the negative 2 power. So clearly, I want x to the negative 2 power right here. So I need n starting at negative 2. So that way it's x to the negative 2. But now, if I go over here and I plug in n equals 0 to that first term, I should get 0. So in this very first location right here for this first term, I'm supposed to get a 0 there. Well, how can I get a 0? I'm going to have to do n plus 2. So that way I get the negative 2 plus 2 gives me a 0 for that first location right there. Okay. Now I'm going to go to the next one, which is n minus 1. Well, if I plug in 0 right here, I'm going to get a minus 1 right there. So that this term is supposed to be minus 1. Well, how do I get minus 1 there? I'm going to have to do n plus 1. So that way when I plug in the negative 2 right here, this becomes a minus 1, just like that one there. Now we have a sub n. Well, we've already sort of looked at what we do with our n's. We're supposed to just do n plus 2. So a n plus 2. And then we have our x to the n, which I had to erase just to make some room. But this is essentially the exact same thing. The third step is to align the series indexes where n is equal to the same thing. As an example, let's see how we could take this n equals negative 2 and switch it back to n equals 0 while still maintaining x to the power of n over here, which is really important. Okay, so all we're going to have to do is we plug in negative 2 right here. All right, and that's what we're going to evaluate it at negative 2. So if we do that, we're going to get a 0 for this whole term, right? So let's just write 0 here. So now this thing is supposed to be, let's evaluate the next term. It should be negative 1 for the next n, right? So let's add the next term. If we plug in negative 1 right here, we're going to be getting, it's another 0. Great. So we have 0 plus 0. And then now that we're at n equals 0, let's rewrite everything here. So we get the sum n equals 0. And then we're literally just going to rewrite all this back in, n plus 2, n plus 1, an plus 2, x to the power of n. So all I've really done here was evaluated this series at n equals negative 2, which happened to be 0, n equals negative 1, which happened to be 0, and then n equals 0. Well, I'm just going to rewrite that there because now I can go back and add this one with this one because I have n equals 0, x to the power of n equals 0, x to the power of n, and we're good to go. Now, the ideal situation in a homogeneous equation, we get something like this. We have the sum of, maybe we'll start at n equals 0. It doesn't have to, but it's a common place to start. And then we're going to have some sort of thing like, I don't know, a to the n plus 2 minus a n. And then we're going to have x to the power of n. And since it's homogeneous, this is supposed to be equal to 0. That's essentially step 4, is that we had to combine, all 3 of these. We're combining all of them into one series. Combining into one series. So that's essentially what we got right here. The next step is to realize that if this equation is supposed to be equal to 0, then just the coefficient itself is supposed to be equal to 0. So what we're going to do is we're going to set the coefficient equal to 0 of x to the power of n. So we simply have this thing right here equal to 0. That sets us up for step 6, because what that's essentially going to give us is some equation where we kind of see, like, I don't know, an plus 2 is supposed to be equal to some question mark here times an. There's going to be more than just that in there, but you're going to get some relationship between an plus 2 and an. So your goal now is to write out the a sub n terms, and we're going to be doing that for both evens and odds. Let's start by writing out some even terms. What we're going to want to do is we're going to start with our n being equal to 0. So we're going to plug in n equals 0, and we're going to get like a2 is equal to some form of, so a2 is equal to something times a naught, right? That's what we would get over here. Now, since we're dealing with evens, we're going to skip the 1, and we're going to go straight to 2, and we're going to plug that in there. So we get a4 is equal to some question mark times a2. Well, it turns out that a2 is just question mark a naught. So we kind of have like double question mark a naught, right? So that was just a2 right there. And we could repeat this, and we can go into the 4, and then we're going to get a6 over here, a6, which is equal to some question mark times a4, which is supposed to be equal to all this stuff right here. So we can put question mark times question mark a naught, and you can see where this is going. We're getting some kind of a pattern here. Let's also do this for the odds. So we're going to start at 1. It's the n equals 1 right there. So we plug it in, and we get a3. We're starting with a3. That's going to be equal to some question mark a1. And of course, we're just going to repeat this process for 3. And we get a5 is going to be equal to question mark times question mark a1. And if we do the same thing with 5, we get a7 over here, which is equal to question mark times question mark a1. Awesome. We wrote out some patterns for the odds and the evens. And finally, the next step that we're going to be able to do is to essentially, we want to be able to write a new n series, and I'll put it a purple n. This is the n series for both the evens and the odds. Evens plus odds really is what we're doing. Evens plus odds. So this new n series is different from these n's. These are blue n's because we use the blue n's to figure out what our terms a2, a4, a6, a3, a5, a7. But now we're going to create a new n series, so we're going to start at n equals 1 right here. And then we have n equals 2 and n equals 3 right here. So we can see how they match up, 1, 2, and 3, instead of being 0, 2, 4, and 1, 3, 5. So we can write a new n series. The form of the final answer here is going to be y. We're going to have evens on the left and then odds on the right. And let's start by writing out the sum of the evens. We'll start out this new series going from n equals 0. We're talking about this type of n, the purple ones. So we start with, let's go to infinity. We're going to go a2n, and then we have x to the power of 2n. So that way, we plug in 0, and 1, 2, and 3. We're just going to get, a naught, a2, a4, a6. So that's going to give us our evens. And then on the right, we're going to add in the odds. So we'll have the sum from n equals 0 again. This is going to infinity. And then we'll go a 2n plus 1. And we have x to the power of 2n plus 1. And then, of course, you have whatever question marks, other stuff, the constants that you throw in there. Or you can put them outside if you want. So this is going to give us our evens on the left and our odds on the right. Plug in n equals 0, we're going to get a1 x, and then a3 x to the third, etc. In fact, that's the last step. We're going to want to write this out in terms of the regular y equation. So we'll plug in n equals 0 here, and we get a naught. Okay, and then the next term is going to be this one. N equals 0 here gives us an a1 times an x right here. Let's go back to this and plug in n equals 1, giving us a2 times x squared. Oops. Okay, so we had x squared. This one doesn't have one. Let's go back over here, plug in n equals 1. We're going to get a3 times x to the third. And now you can see how this is built out. Well, we really want to plug in our initial conditions at this point to be able to figure out maybe what these 8 terms are. And that should be how we can solve our series.